So nerves, we know, talk to each other. Okay, they make communication. And this communication is electrical, but the electricity, the flow of the electricity or the electron is in the axon of the nerve. But one nerve has to talk to another, and it talks to it by the secretion of a chemical. And that chemical is secreted at the terminal end of one nerve, attaches to a receptor site in the next nerve, and opens a channel or a doorway up to start the electricity flowing again. So this all occurs in a fraction of a second. So the nerve is called a dendrite. So here we've got the neuron part of the cell body, and then we've got the, let's make sure we got that. Then we've got the axon, which is like the flex or the cord, and the tail end, which looks like a bit of bladderwrack seaweed at the end there. We now know that neurons have multiple connections, that the idea originally that one nerve talked to another nerve is now not known to be probably the case, that on the terminal end there's possibly hundreds, if not more, dendrites and neurological connections, that one nerve can connect to multiple places. So the whole brain is very holographic. So you can't say, oh, this particular neuronal circuit is strictly noradrenaline or is strictly serotonin. Everything is there in all of them. Okay, so one nerve can transmit, but it depends what it attaches to, or what it makes those secretions at the terminal end, and what receptors are available. And the receptors are very, very important, because if the receptors are working, it'll take up the serotonin or whatever it is and allow it to work. So don't think of it strictly as only one nerve, one communication. In other words, if I lift the phone up, I can talk to Paul, but at the other end of the phone could be a whole load of other people. Now, they may not be able to hear because it's encoded, or they may be able to hear, so it just depends upon who's got the receptors, the right ears to listen to me. So we said that down there. Neurotransmitters are chemicals. We know that neurotransmitters produce their effects by releasing into synapses and then attaching to the receptor sites. We divide, or it's divided into three types of neurotransmitter. And these are easy to remember. They're excitatory. These are particularly ones like glutamate or glutamic acid and aspartate or aspartic acid. They can be stimulatory, which I prefer the word regulatory, because these are the ones that keep us going on a regular day-to-day basis. And they can be inhibitory. In other words, they can fail to switch the next nerve on purpose. These would be things like, as we'll see, GABA and glycine and taurine. So there are other neurotransmitters that also affect signal transducing inside the cell: cyclical AMP, cyclical GMP, phosphatidylinositol. These are known as secondary messengers. So 10 compounds make up the three families: the excitatory, the stimulatory, and the inhibitory. And they're divided up into these different groups. So that makes, you'll find, 10. But some of them work on the same meridian. So excitatory neurotransmitters is aspartic acid or aspartate. Okay. This is not aspartame, although it does contain aspartame. So aspartic acid and glutamic acid or glutamate. Okay. So those are their excitatory ones. Then our regulatory stimulatory ones are acetylcholine, which primarily regulates our parasympathetic nervous system, in other words, the day-to-day working of the body. Noradrenaline, the sympathetic system, particularly when we're under stress. And dopamine, serotonin, and histamine. So these are the ones that keep us on a regular par. And then our inhibitory ones are GABA, glycine, and taurine. So we'll come to know those words quite well. So in addition, there's certain other substances that can work as neurotransmitters. Adenosine, enkephalins, which are like the opiate-like substances in the brain, and endorphins, and even nitric oxide has been shown to have a neurotransmitter effect. So glutamic acid and GABA are the most abundant neurotransmitters in the central nervous system. Okay? So more than anything else, humans are different. Humans are different from all other mammals. And we're different in one particular way, and that is that we've got a frontal cortex which has been activated more than just the prefrontal cortex and the basic motor neurons. We've got this big frontal lobe or orbital frontal aspect to it. We've got a forehead. If you look at an ape, which is our closest relative, or possibly a dolphin, they're sort of cut off across there. They don't have a forehead. Okay? We've got this forehead, and the more you think, the bigger your forehead. This is why a big head and a big forehead was always considered to be a sign of a genius. Okay? Now we know that that's not strictly speaking, because the size of the brain doesn't matter, it's what you do with the brain, isn't it? And people who use a lot of thinking, come on regular courses like you do, get bigger frontal lobes. Okay? Einstein had big frontal lobes. If you look at a picture of him, he had big frontal lobes there. Okay? But interesting, so do meditators. The more people meditate, the bigger their frontal lobes become. And the frontal lobe has been shown to have more receptors of endorphins, or opiate-like receptors, than anywhere else in the body. So you can get good things happen in your frontal cortex by thought process. But you can, if you're thinking negatively, you can also create other problems. So glutamic acid is very rich with receptors in the frontal cortex, and basically it's excitatory, and sometimes you have to put the brake on excitation. You don't want to act spontaneously, sometimes you've got to think and say no. So the one that says no and switches the brain off, if you like, or inhibits it, is GABA. So think of it as GABA or inhibition saying no, and glutamic acid saying yes, yes, yes. Okay? So that's the difference between the two. So when you do something and you want something, and I often say, you know, an example of this would be your telephone. I'm going to take your telephone. I want it. That's my glutamic acid. And then my part of me says, no, that would be wrong because this belongs to you, and says, no, I mustn't do that. And that's the GABA part. Okay, so we've got a balance between the two with decision making, which is what the frontal cortex does. It's involved what's called the executive center, or making decisions. So every neurotransmitter attaches to specific receptors. And we've got to branch a little bit away from thinking just these receptors are only in the brain. We'll be talking about this, but on the other hand, we've got to realize that the receptor is on every cell in the body. And we may see this on the neuron. We may see it on the white blood cell. We may see it in a liver cell. All our cells have receptor sites, and some have bigger receptor sites for certain chemicals than others. But these brain chemicals are not just in the brain. They flow out of the brain, out of the cerebral spinal fluid, down the tracts of nerves, and have been shown to be in every area of the body. So the electrical charge that goes down is quite simple. It's a matter of whether the cell is polarized or depolarized. So it has a normal resting potential, in other words, if you stuck a voltmeter in there, of minus 70 millivolts. Now, minus is when the electrons are flowing, so this is charged up. So if we increase the negativity, we would make it more polarized or hyperpolarized. Okay, so this would stop electricity from actually flowing. If we neutralize the minus 70 and make it 0 or even plus, this will discharge the electron down there, and this is what we call depolarized. So to actually send the message down, we need to depolarize the electron, the charge there, and change it from minus 70 to 0 or even plus 70 there. So when we add another negative here, we've got to have something which can do that. And well, the thing that does that more than anything else is chloride. So chloride has a negative charge to it, so when chloride goes into the cell, it adds another negative, which increases the polarization and inhibits the depolarization. And this is why they're called inhibitory neurotransmitters. So you've got to stimulate an inhibitory neurotransmitter to not fire the next nerve. Okay, so they use chloride. So if we want to add a positive to make it discharge, we need something with a positive ion on it, like sodium or perhaps calcium. Okay, so when sodium or calcium enters the cell, it increases the positivity. In other words, you lose the negativity and the electron then fires. Okay, so this is called polarization. So in the stimulatory neurotransmitters, we use sodium and occasionally calcium, as we'll see when. And the inhibitory neurotransmitters, we use chloride because it's got a negative one. Okay. So when we use calcium, calcium appears to be used in addition to sodium in the excitatory neurotransmitters, but not so much in the normal regulatory ones like acetylcholine. So calcium enters in the state of excitation much more. And I think the reason for this is calcium's got two pluses, so it increases the depolarization much faster than just sodium on its own. But what we do know is that if you increase calcium and sodium within the cell, it has to be pumped out. You can't just leave it in there, otherwise the cell remains discharged. So for every positive ion that we put into the cell, we have to pump it out. And that pump is an active pump. In other words, it uses energy. It's not passive, it's active. And we have to pump out. And that's why we need more energy or ATP produced in the neuron than anywhere else in the body. Okay? The brain is the most energy, oxygen-hungry tissue in the whole body. So energy, ounce for ounce, if you like, kilogram for kilogram, is more used in the brain than anywhere else. Followed by, of course, the muscles and then other cells eventually. So most cells in the body only have one mitochondria or powerhouse. Muscles have multiples, but the brain, the neuron, has hundreds, if not thousands, of mitochondria, simply to generate the amount of electricity to drive the pumps to pump out the sodium. So if you don't have enough energy and you overfire the excitatory ions of the calcium, calcium will get into the cell, and eventually, when it builds up to 20% or more, the cell dies because you turn to stone. In other words, you build up the calcium, and it's at that point, called transneural degeneration, that you're in trouble. Because that nerve, once it's died, has died, and without stem cell therapy or stimulation of stem cells in the body, you can't replace it. But luckily, we now know that nerve cells do replace, but at a much slower rate than what they degenerate. But nonetheless, it is possible to do this, and we'll look at substances as we go through the different modules that can do this. So excess activation of receptors in neurological diseases can cause toxic quantities of calcium to enter the cells and to kill them. Now, we know neurotransmitters like acetylcholine are broken down once they've done their job on the neurotransmitter, once they've done the job on the receptor side, and basically broken down to their components and recycled. So we don't use very much of it up. We lose only minute quantities there. Some of them go through a reuptake process where the same neurotransmitter goes round to a receptor site on the original nerve and is taken back up. And we're probably familiar with this with the selective serotonin reuptake molecules of serotonin. So serotonin is not broken down actually in the synapse, but is retaken up. And we're familiar with a range of drugs like Prozac, which block those receptors, so the serotonin level remains high. And that would be a pharmaceutical approach, which is great for some people, quick-acting, antidepressant, or what it was thought of. Unfortunately, it doesn't solve the problem why the person's serotonin is low. So in the long term, we need to help that patient to make serotonin rather than just blocking the uptake of it, okay, or reuptake of it. In the long term, we need to help that person to make their own serotonin. So the function occurring in the terminal end of the neuron is very similar for all the neurotransmitters. So if we use acetylcholine as a good idea here, as a model, then we can use this for all the other neurotransmitters. So we actually make the neurotransmitter at the terminal end of every nerve, okay? It's nothing to do with what we eat. We can eat acetylcholine, but that won't make the brain produce it, okay? It has to produce it, and it has to produce it from the raw materials, okay, from the components, the substrates. And the two substrates for making acetylcholine is acetyl, from acetyl-CoA, the active form of B5, and choline, which is one of the so-called non-essential vitamin Bs. So when we blend those two with a particular enzyme that we'll see, we make acetylcholine, and the byproduct of this is the CoA, which is redistributed. Okay? So it's the acetyl part we need. So ACH is acetylcholine. This is then, once it's produced, is stored in little vesicles. And we know that all the organelles within cells are covered in cell membranes, okay? And all cell membranes, as we learn, are made of oils, okay? So even these little vesicles are made of oils. So at the terminal end of the nerve, microscopically, we've got vesicles which contain the acetylcholine ready for action. Now these vesicles then move when the nerve is depolarized to the cell membrane of the nerve, and they blend with it, like putting two bubbles together. If they're of the same composition, two bubbles will blend together and pop and produce one bubble, okay, in the bath. But if one bubble contains a different substance, so you put one detergent in your bath and in one end and one detergent in the other end of the bath and make some bubbles, those two bubbles probably won't mate, okay, they'll stay as two individual bubbles. And this is what happens if the constituent fatty acids of our bubbles are different from our cell membranes. Okay? They can't work. And this is what happens in kids who can't get their brains to function. So the solution to this for a lot of kids was, oh, stick them on, they found omega-3 oils are very rich in the brain, stick them all on omega-3 oils, and some of them improved, which is great. Some of them improved with omega-6 oils, like evening primrose and so on, but they know omega-3 oils are rich in the brain, so by increasing the omega-3, you would then put in new oils and get the balance in there, and many kids respond very well to this, and their work and their concentration and behavior improves, and this is why. But there are downsides to that again, because omega-3 may not be the one that they need, the fish oil. And as we learned in previous modules, people who weaken to the colour blue are very sensitive to mercury. They cannot detoxify mercury. And with toxic metals, if you can't detoxify them, what do you do with the metal? You store it. And where do you store it? In the fat. And what's the brain made of? 30% of dry weight of the brain is fat or lipids. Okay? So most people will store toxic metals and other chemicals that they can't detoxify in the brain. Okay? We don't know whether that has a detrimental effect or not, and this is the problem. But blue people do react, and therefore blue people should not eat fish oil. Okay? So ramming fish oil into a child who has a blue genetic constitution is just adding low levels of mercury over a long period of time, and will probably ultimately decrease their brain function, not increase it. Now, people years ago used to go mad when they increased their mercury in their brain, and that was why they were called the Mad Hatter, all right, because the felt making in the hat was had a lot of mercury in it. So they literally went mad. So if you see somebody in your family or as a patient who you think they're as mad as a hatter, they probably are as mad as a hatter. And if they're blue, think mercury, right? And think, what is the major source of mercury? The major source of mercury these days is fish oil, okay, and other factors like the new bulbs and things are all full of mercury vapor, probably more than the dental amalgams. There's other sources of mercury coming in. Okay, so what happens? The acetylcholine is then liberated into the synapse here, attaches to a receptor site, allows the sodium or calcium to go in if it's an excitatory, so the next nerve depolarizes, and if that's a muscle, the muscle will contract. And the acetylcholine is then broken down by an enzyme called acetylcholinesterase, in this case, to acetate and choline. And those are then taken back and recycled. So we don't need too much of these compounds, but we do lose a little bit because there is no membrane here. There's nothing sealing this unit. This unit is within the extracellular fluid of the brain. So a little bit of acetylcholine and some loose choline here and acetyl will float in between the cells. And that is, the fluid in there is called cerebral spinal fluid. And that cerebral spinal fluid we now know flows down the axons of every single nerve and tubule within the connective tissue of the body. So this is how you can produce acetylcholine in here, and eventually you'll find it will come out in your big toe. There'll be connections, so we make those movements. Every time we fire a nerve, we get the short-term electricity effect, but we get the long-term travel of the neurotransmitter down the axon, which stimulates and activates the nerve and the muscle, the target, for a lot longer period. So that model of producing it in the terminal end, firing it off through the vesicles there, recycling it, is the whole process for all the neurotransmitters. So that's just summarizes what I've been talking about. Now, the receptors where it attaches are like docking bays. So the neurotransmitter goes in, it locks into the docking bay, and then it opens the gates of the lock, if you like, up. They open, and that allows the sodium or the calcium to go into the cell. Okay? So there's little guards here, these gates, stop too much from getting in and out. And these are very important when we come to certain neurotransmitters to find what these ion channels are regulated by. And in certainly the excitatory ones, will come there that realize that one of these is magnesium and the other one is zinc. So magnesium and zinc are two very, very important elements or minerals within the regulation of the receptor site in the brain chemistry. Very, very important. And both of those are the most common ones that are deficient in humans. And the reason probably that they're deficient in humans most of it is intensive farming, that those minerals are never replaced in the diet. Clive, for years we've done the zinc taste solution. So if we pop out a zinc taste on here, this is still very standard stuff, 0.1 solution of zinc sulfate. Just take a squirt, don't lick the pipette, just put it on in your mouth, swill it round for 10 seconds and swallow. And the general concept was if you can't taste the zinc, you're zinc deficient. If you get a vague taste, that's good. If you get a real strong, horrible, dry, rhubarby taste, that's excellent. Okay, that means your zinc is probably all right. But if you just pop one on and have a squirt, but don't lick the pipette because the next person is going to do it. Okay, just hand it on to the next person, all right? And it's a bit of fun. And the incredible thing is just how many people are zinc deficient, okay? And we do find generally, when we do this, you will find something like 50 to 2/3 of the room will be zinc deficient. So there's a number one substance vital for your whole functioning of the brain, which we're already, most of us are not working well enough with. So these functional tests remain, really, really important to actually take. So put it in your mouth, hold it there for 10 seconds, swill it round so it gets on all those taste receptors in the tongue, and then swallow it. Okay? Now, neuronal membranes are different, in other words, the membrane around the cell, from other cells in the body. Now, all cells are made primarily of fats or lipids, and these are complex substances. They're not, your straight DHA, EPA popped in and that's it. They're complexes, and they're complex with other substances, and they're called phospholipids. So they're obviously bonded with phosphate groups and other compounds. So they can be phospholipids, they can be glycosphingolipids when they're attached to sugar molecules, and they can be lipoproteins when they're attached to protein substances. So it's very complex, the way the membranes are made. So we know that simple lipids or fats are made of single ones and multiple ones. They're saturated, which means you've got a straight chain, like here, with a methyl group at one end and a carboxyl at the other. Or they're unsaturated, which means they've got one or more double bonds. Okay? Now, it's the double bond ones where we've got problems. Double bonds mean that we can attach something else to that. And this is the trouble, that a double bond means that the double bond can open up instead of being attached to the next carbon and hold on to something else. So a double bond potentially could hold on to a metal, but more important and the most obvious thing that it tends to hold on to is oxygen. Okay? So a double bond will open up and an oxygen will become attached to it. But this oxygen only has one attachment, and oxygen should have two attachments, which means this is a radical. This becomes a radical or a free radical or reactive oxygen species. So when an oil or a fatty acid becomes oxidized, okay, it basically, we call it, or you call it, rancid. Okay? It becomes rancid, it becomes oxidized. And this, unfortunately, is what happens to most of the oils, which go through a heating process in the extraction of what you eat. So when you eat commercially produced oil, and you fry your breakfast and your chips and things with that, in the majority case, this has already gone rancid. It's got a smell to it, but you don't smell it because they add a fragrance. Okay, very clever. Okay, they hide it. If you get a cold-pressed oil, which basically means below 100 degrees in the extraction process, the oil will be intact. So rule number one, when somebody takes a fatty acid or an oil into the diet that you prescribe, they must not put it on hot food. Certainly number one is they don't cook with it. Okay? Number two is you do not put it on hot food. Okay? You put it on the temperature that you can eat it, which basically is 70 degrees or less. So if you're taking a casserole out the oven, don't pour the oil onto the casserole, right? Because the oil will go rancid straight away, and then you'll increase your rancid fat levels. Now, rancid fats have been shown to be more like ping pong balls rather than bubbles. So ping pong balls don't absorb nutrients or pass debris out. Okay? So you'd rather have a bubble as your cell membrane, particularly in your brain, than a ping pong ball. Okay? Now, luckily, oxidized fatty acids are changing all the time. So we're changing our cell membranes over. Our fatty acids, our oxidized ones, are being changed to new ones all the time, providing you've got the new fatty acid in your diet, or that you can make it. So the question is, what happens if you don't get that in your diet? You just accumulate, basically, old oils, oxidized oils in the system. And this is what happens as we get older. And this is why fatty acids are the first thing that you actually find when degeneration is outpacing regeneration. Okay? So one of the interesting things I found that when I started doing this a month or so back is in the morning time, I like to go for a bit of a run, you know, most of the mornings there. And when I come back from the run, what I usually do is just do a couple of minutes, you know, and I go down and try and touch the toes and that sort of thing, you know. And you do it about 6 times, and eventually you can get down to the ground. And I found after a couple of weeks of taking the right oil, I could go down straight away and put my hands almost flat down. And I thought, this is not me. You know, I've got tight hamstrings, tall, 6'1", and so on. So what I want you all to do is to stand up, okay, and just gently go down. Don't worry if you can't touch your toes, that's not an issue, okay? Just get a feel of your range of motion. And this is the first thing that you will find will change if you're going to do a rejuvenation program. Okay, so just go down what is comfortable. Don't try and, you know, show off. Just go down comfortably. Do it a few times and see how far you can get. And then just remember that, so that when you've done your regime, as you sort of do the right oils and things over the next month, so remeasure it and think, oh yes, I am much more flexible. Because if you're stiff in your range of movement, your membranes are stiff, okay? Not just in your brain might be stiff, but your legs are stiff, your ligaments are stiff. All the cells in your body are made of these oils. So this is the first thing that you see. Now, in previous seminars, we've talked about the embryological ectodermal tissue of when the fetus is developing. Ectodermal tissue divides into 2 tissues in the body, which remain intimately connected all your life. One is the brain, or the central nervous system, and the other is the skin. So the skin and the brain are ectodermal embryologically and remain intimately connected, which is, I'm sure, why working on the skin, the acupuncture points underneath the skin thing, affect the brain chemistry. Okay? But more important is, let's have a look at the skin. Ask yourself, do you have any problems with your skin? Do you have any dry areas? Do you use a body lotion because you're generally dry? Do you always have to put skin cream on certain locations because certain patches are dry? Okay? Do you have any skin problems at all? Do you have eczema? Huh. How many children do you think? Well, I wonder what the percentage of children with eczema is now. What do you think? I think it must be 25% at least of children, you know, say under 10, have got or had eczema at some time. Psoriasis, you know the skin problem. You're looking at essential fatty acid problems with these people, okay? Look at the diet. How on earth do people get all the essential fatty acids in from the diet that most kids are eating? Now, we know in addition to oils going rancid and us going rancid with the aging process, that oils can be heated and very often are and used for cooking purposes. And what we find is the double bond, the molecule here can twist. So a double bond, or here, in this case of an unsaturated, has a bend in it because there's a hydrogen missing in the chain. So we have a bend, okay, like that. And if we've got a polyunsaturated oil, we've got lots of bends in there, okay? Now, if you heat the vegetable oil, the molecule twists, and if you heat it above 100 degrees C, it will twist and it straightens out. And an oil that straightens out acts more like a saturate, which increases the melting point. And this has been shown to occur with most Western people, is our melting points are going up. So we need global warming to melt again, okay? Okay? So our body-to-body melting point has gone from 27 to 31 degrees. Okay, so we're becoming more solid, okay? So what does the fish do? The fish in the North Sea and places has a lot of polyunsaturated, which have low melting points, minus 13 and minus 15 EPA and DHA oils, and they keep you flexible, okay? So we need to increase our good oils to become more flexible. So the only way you can get rid of these heated oils, or trans fats as they're called, is to have a diet rich in cis fats, or the ones with the bends in it, okay? But remember, you mustn't heat them. So 2 golden rules is you must have, very important with the right oil, is you must have cold pressed. And you must have organic, because you don't want to take pesticides, oils that have got pesticides in it, residues in it, because remember, all chemicals and pesticides and toxins store in oil, whether those are vegetable oils or human or animal oils, okay? You must have organic. Because if you take chemicals in, you're going to generate more reactive oxygen species or oxidative reactions to detoxify the chemicals. And then you're back to square one again, okay? So they have to be cold pressed and they have to be organic, okay? So that's the importance of unsaturated fatty acids. And you will find that's the #1 thing with the regeneration program, is a lack of the right oils. Okay? But the $100 question is, which oil? Is it for you? And which oil is it for me? And so on. And the answer is, I can't tell you. But I can test you for which it is, but there is no way of predicting. But when we come to look at them, I will tell you that certain oils seem to fall into patterns with people, and it's very early work with this. Now, which are the common oils that show up? We know that the body can make most unsaturated oils. Most texts will tell you that linoleic and alpha-linolenic are the essential oils, and from those you can make most other ones. We are convinced that with the addition of vitamin D, which you get through the use of the mirror glass so that the ultraviolet goes through and converts any cholesterol into vitamin A, you can make most of the oils in the body that the body needs, including the omega-3s. So from 2 vegetable oils, which is peanut and sesame, you can make the majority of oils. Okay? But there are certain fatty acids which clearly you have to get from the diet. Okay? You can't make for whatever reason, and I can't tell you what they are. Okay? There must be probably hundreds, if not thousands, of possibilities of different structured oils within the human body. That all we've given emphasis over the years, like everybody else, is to the omega-3, EPA, DHA, and the omega-6 evening primroses and so on. And then we shut the book, okay? And we've never looked for anything else, and we've assumed that if a plant oil shows positive results, it must be because it's got GLA in it or EPA, etc. But in fact, it's not, because I discovered this years ago that if a person needs GLA, they should strengthen to any source of GLA. Blackcurrant seed, evening primrose, borage, starflower. They should strengthen all 3, didn't they, if there's GLA in that. And the same with EPA and DHA, but they don't. So some people strengthen to one oil because they've got something in that oil that isn't in the other oils. Okay? Now, there are some people who strengthen to 2 or 3 different types of oils, but the majority of us only strengthen to 1. And this particular oil might be one that is in your diet, and on the other hand, most of the time it's not in your diet, which is why you're getting old. Okay? So you might want to just jot these down. When we've done this and we've gauged it with degeneration against regeneration, we found that surprisingly fish doesn't show up, fish oil, and nor did things like evening primrose. So this is not in alphabetical order, but I'm going to just get you to write them down, because there are 10 oils which seem to show up, 1 or more of these, with every single person. Now, this is not alphabetical. Walnut is the first one on this list. I can't tell you what sort of problems walnut shows up for, but it's a lovely oil. French are very keen on it. Second one in here is hemp seed. Hemp seed oil definitely shows up in every case I have tested it with type 2 diabetes. So there are fatty acids within hemp which get incorporated in and activate the ability for insulin to pass through. Number 3 is pumpkin seed. If you get the opportunity to get Austrian pumpkin seed, that's the loveliest. That's almost like thick treacle. That's really, really lovely. But again, all these oils have to be cold pressed and organic. Grapeseed, and this was a big surprise here. Grapeseed obviously comes from the pippa, the grape, all right? And this one shows up in all cancers, all malignancies. Okay, it doesn't mean that everybody who strengthens to grapeseed has got a cancer. But everybody who's got a cancer or had a cancer, you'll find will strengthen to grapeseed. Okay, so there's something in grapeseed which allows their receptor sites to work much better. Okay, sunflower. Common garden one, people say, oh, I can buy that anywhere, can't I? No, you can't. You cannot buy organic cold pressed, probably more than any other oil you can, but be very careful, because sunflower is often, highly trans fat because it's not cold pressed or organic. Flaxseed, again, or linseed. If you're really unlucky, this one comes up. Most people's mouths drop when that's the one. It comes up a lot with eczema and other problems, but it's certainly an acquired taste, isn't it? They've known for a long time, a lot of German research in treating malignancies with flaxseed oil regimes and cottage cheese and things. It's an old remedy there. Okay, so then sesame, one of the 2 in the wonder oil, sesame seed oil and peanut oil, but sesame, probably of all the 10 fatty acids, is the one that shows up most commonly. So I would say that's the most common one in my practice anyway that I found is sesame for all sorts of multiple problems. Olive, again, comes up. Probably not the most common because we're sort of Northern European. It's not a natural one, but it does come up. And then we got hazelnut. Now, hazelnut comes up with a lot of visual problems, but again, I'm not sure specifically what clinical problems you're going to find hazelnut. But again, a wonderful oil, and peanut. And those are the ones that show up. I haven't found any of the other ones. In here we've got rice bran oil, which we were at the Good Food exhibition yesterday in Birmingham, and it's the most disgusting stuff. They say, oh, you can fry with this, it has no taste. It doesn't have a taste, but boy, it affects your gallbladder afterwards. And we said, oh, are they, that and rapeseed. They're doing a lot of rapeseed because they're polyunsaturates and you can heat them without turning into trans fats. Are they organic? Oh, yes, they're all organic. I said, but it's not on the bottle. Well, no, actually, they're not organic. So all these oils, people think that they're all unrefined, refined, all lovely words that they put on there. But really, you've got to get to the nitty-gritty, and the nitty-gritty is organic and cold-pressed. Now, a little later on, I'll tell you about the problems with the EU and the labelling with organic, but certainly they've got to be cold-pressed. And unfortunately, because of the EU regulation, the word organic is being restricted. But you can find other ways that it is organic. Okay, so those are the most common ones. So I'll do some demonstrations as we go along and try and find and identify what is the right one for you. Those oils are in the old fatty acid kit, and they will be available in charcoal in the next kit that we're doing, which is a nutrition type of box. So those oils and all the vitamins and the minerals and essential things will be in there. So fats within the cell membranes are basically unsaturated in the brain, and half are going to be saturated and half going to be unsaturated in every other cell membrane in the body. So I'm just going to whip through this because we don't want to get tied down time-wise. So a phospholipid is like a tadpole. It's got a head, which is usually this part here, and it's got two tails. And most of them have a tail which is straight, which is a saturated oil, and a tail which is unsaturated, so it has a kink in it. So if, for instance, you had a trans fat in the unsaturated position, it would look like two tails which are straight. So the melting point would go up and the whole oil would be harder. And similarly with the oxidized fats. So oxidized and trans fats act more like saturates and increase the melting point and therefore decrease the function, the fluidity of the membrane to allow nutrients in and out. So that head might be choline, it might be inositol, it might be ethanolamine, serine and threonine. So these are called the phospholipids, and we're all familiar with phosphatidylcholine, phosphotidylserine, etc. But that kinky tail there, all right, see, is attached on the end of the methyl group, the carboxyl end of the fatty acid. And this allows any oil to attach on there with the code for that particular fatty acid, but it doesn't worry if it's trans, oxidized, or cis. It'll take it up. So if you've got a high level of oxidized and trans fats in your body, in your fat, in your lipids, in your blood and your lymph, you'll take that up. So the body doesn't know the difference between the two. Okay? So your only way of getting rid of high levels of oxidized and trans fats is to increase the cis form, okay, so within your diet. And these are changing all the time. And why are they changing all the time? Because oils get rancid. They get oxidized by free radicals. So we need to know what is the main protector to the unsaturated fatty acids in our brain and other cell membranes. And this again was the second surprise with looking at the aging process. In 100% of cases, what that was. And of course, the first thing you jump to is vitamin E. And it wasn't. Okay. Vitamin E is not the main protector of lipids in the body. Okay. It is a protector of lipids, but it's not the one. The one, without any doubt, in my opinion on there, and the finding, is glutathione peroxidase. And glutathione peroxidase is recycled by an element called selenium. And selenium, where in areas of the world where people live the longest, is where the selenium level is highest. Okinawa, Lake Baikal, the Hunza Valley, Peru and the Andes have all been shown, even Lourdes has been shown to be high in selenium. People who take the water from Lourdes home and drink that for a few months are the ones who maintain their status of health much better than the ones who go there, partake of the waters, and then go home. If you go to these places, always take the water, okay? And nobody knows what it is, but now they've discovered that they're all high levels of high selenium, okay? So with the places like Lourdes, if you get the opportunity, there's a place north of Lake Como. Again, they usually got natural sanatoriums for healing for people. They feel wonderful. Then they go home to their towns and all their illnesses come back, okay? So remember what the difference is. Take the water home with you, but the key ingredient here seems to be selenium. And you will find every time a person shows to a fatty acid, which is practically all of us, you need selenium to protect it, okay? And the type of selenium is really important, and that type of selenium is basic selenium as a sodium selenite compound. Nothing complex, nothing to do with selenium methionine, not linked to amino acids, just raw selenium that can be taken up. And that selenium, the richest source of that selenium is, what was it? Watercress. You're right, absolutely, it's watercress. Okay? So again, I was brought up, mother eat watercress, so I hated it. It was too sort of bitter and everything else. But now I can see, the value of watercress. It takes you years and years before you come to realize that your mother was probably correct in these things. Okay, so a little bit of watercress. We find spinach is quite good as well. Although spinach, you tend to if you eat it raw, it's all right. If you tend to wash it, if you tend to cook it in water, it disappears, and probably the selenium goes into the water. So watercress is better. Again, organic. Now, there's another reason, not only the glutathione peroxidase for the water, for the selenium, and this is probably more important than even that of why selenium shows up, is there is an enzyme that cleaves or cuts out the oxidized fatty acids in the membrane, and this is called phospholipase family. And I believe, and it's only me who believes this, but I've got a good biochemical colleague, Igor Bondarenko, as you know, who works and helps us, that phospholipase is a selenium-dependent enzyme. If this is the case, what it means is the selenium that you take in the watercress or as a supplement stimulates the enzyme which carves off the old oils. And providing you've got the new oil in place, it can put it in. Okay? If you carve off the old oil and you haven't got a new one, what do? You put in any old rubbish in there, okay? Which it could be the same fatty acid, but it's oxidized or trans state. So the selenium goes with it, and that gives you the two major things. And both those take every single person I challenge, not only from their degenerative state, but they take them to plus 10. Okay? Doesn't mean they're going to be plus 10, but for that process, they are going through a regeneration program. And it will take you probably 3 months. Your body changes over, all the oils and things in your diet every 3 months, probably maybe longer, but you'll see dramatic differences in 3 months. Okay? Not by tomorrow. Okay, so warn people, but if you think about it, you've got 50-odd trillion cells. Every one of those has got a cell membrane. Every one of those has got internal organs with membranes, and they've all got to be replaced. Okay? So it takes some months to do this.